Water is the lifeblood of our planet. It sustains us, shapes our world, and governs our weather. Ever present, its dance takes countless forms, from the gentle ripples on a pond to the crashing waves of the ocean. Understanding the movement of water, this essential substance, is to grasp a fundamental force of nature. It's a realm where physics and poetry intertwine, where science unveils the magic in the mundane. Consider the graceful arc of a waterfall, a testament to gravity's pull and water's fluidity. Picture the swirling currents of a river carving canyons over eons. Imagine the delicate balance of a water strider, seemingly defying gravity as it glides across the surface tension of a pond. These captivating phenomena, and countless others, fall under the fascinating purview of hydrodynamics. Hydrodynamics is the science of fluid flow. It delves into the mysteries of how water and other fluids behave in motion. From the smallest droplet to the vast expanse of the ocean, hydrodynamics reveals the elegant principles governing their every swirl, ripple, and surge. By unraveling these principles, we gain insights into the natural world and unlock the potential for groundbreaking innovations. Join me now on a journey into the heart of hydrodynamics, where we'll explore the forces that drive fluid motion and uncover the wonders hidden within every drop of water. Prepare to be amazed by the intricate dance of this life-sustaining substance, a dance that has shaped our planet and continues to captivate our imaginations. At the heart of hydrodynamics lie a few fundamental principles that govern how fluids behave. These principles, rooted in the laws of physics, explain the intricate movements of water and other fluids, from the smallest trickle to the mightiest ocean current. Understanding these principles allows us to predict and manipulate fluid flow, leading to advancements in engineering, technology, and our understanding of the natural world. One of the key concepts in hydrodynamics is pressure. Pressure is the force exerted by a fluid on its surroundings. It's the reason why a balloon inflates when you blow air into it, and it plays a crucial role in the movement of water through pipes, blood vessels, and even the atmosphere. Another important principle is viscosity, which refers to a fluid's resistance to flow. Think of honey, which has a high viscosity, versus water, which has a lower viscosity. Viscosity affects how easily fluids flow and influences the forces required to move objects through them. Surface tension is another fascinating aspect of fluid behavior. It's the force that allows insects to walk on water and creates the spherical shape of raindrops. Surface tension arises from the cohesive forces between fluid molecules, creating a thin skin at the surface. By unraveling these fundamental principles of pressure, viscosity, and surface tension, hydrodynamics provides a framework for understanding the complex and often mesmerizing movements of fluids. Pressure is the unsung hero of the hydrodynamic world, a silent force that drives the movement of fluids in countless ways. It's the driving force behind our plumbing systems, the reason why airplanes can soar through the air, and a key player in the Earth's weather patterns. Understanding pressure is essential to unlocking the mysteries of fluid flow. Imagine a balloon filled with air. The air molecules inside the balloon are in constant motion, colliding with each other and the walls of the balloon. These collisions create a force that pushes outward on the balloon's surface, and that force is what we call pressure. The more air molecules you pump into the balloon, the more collisions occur, and the higher the pressure inside the balloon becomes. This same principle applies to liquids like water. Water pressure increases with depth because the weight of the water above exerts a downward force. This is why dams are thicker at the bottom than at the top. They need to withstand the higher water pressure at greater depths. Pressure differences are what ultimately drive fluid flow. Fluids naturally move from areas of high pressure to areas of low pressure. This is why water flows from a faucet when you open the tap. The water in the pipes is under higher pressure than the air outside, so it flows out to equalize the pressure. Buoyancy is the force that makes objects float, a seemingly magical phenomenon that has captivated curious minds for centuries. From the massive ships that traverse the oceans to the hot air balloons that grace our skies, buoyancy is a testament to the invisible forces at play within fluids. Understanding buoyancy allows us to design vessels that float, predict the behavior of objects in water, and even explore the depths of the ocean. The key to buoyancy lies in the relationship between an object's density and the density of the fluid it's immersed in. Density is a measure of how much mass is packed into a given volume. Objects denser than the fluid they're in, like a rock in water, will sink because the downward force of gravity is greater than the upward buoyant force. However, if an object is less dense than the fluid it's in, like a cork in water, the upward buoyant force will be greater than the downward force of gravity, causing the object to float. This is because the fluid exerts an upward force on the object equal to the weight of the fluid displaced by the object. This principle, known as Archimedes' principle, explains why ships made of steel, a material much denser than water, can float. The shape of a ship's hull is designed to displace a large volume of water, creating enough buoyant force to counteract the ship's weight. Section 5. Viscosity, the stickiness factor. Viscosity is the unsung hero of the culinary world, the silent force that determines the texture of our sauces, the consistency of our dough, and the flow of our favorite beverages. It's the resistance of a fluid to flow, a measure of its stickiness or thickness. From the smooth flow of honey to the sluggish ooze of molasses, viscosity plays a crucial role in our everyday lives. Imagine pouring honey from a jar. The honey flows slowly and resists deformation, clinging to the sides of the jar as it makes its way down. This resistance to flow is due to the strong intermolecular forces between the honey molecules, which create internal friction and slow down its movement. In contrast, water flows much more easily because its intermolecular forces are weaker. Water molecules can slide past each other with less resistance, resulting in a lower viscosity. This is why water splashes and spreads out easily while honey tends to clump and hold its shape. Viscosity is influenced by a number of factors including temperature. Heating a fluid generally decreases its viscosity, making it flow more easily. This is why heating up syrup makes it easier to pour and why warm honey flows more smoothly than cold honey. Section 6. Surface tension, water's delicate skin. Surface tension is the magician of the water world, the invisible force that allows insects to walk on water, creates the mesmerizing dance of raindrops, and holds together the delicate spheres of soap bubbles. It's the tendency of a liquid surface to behave like a stretched elastic membrane, resisting deformation and minimizing its surface area. Imagine a water strider, its delicate legs dimpling the surface of a pond without breaking through. This seemingly gravity-defying feat is possible because of surface tension. Water molecules at the surface are more strongly attracted to each other than to the air molecules above, creating a cohesive force that acts like a thin skin on the water's surface. This skin is strong enough to support small objects like water striders, as long as their weight is distributed over a large enough surface area. The water strider's legs are coated in hydrophobic hairs that repel water, further reducing the force needed to break through the surface tension. Surface tension is also responsible for the spherical shape of raindrops. Water molecules are attracted to each other in all directions, but at the surface there are no upward forces to balance the inward pull. This causes the surface to contract, minimizing its surface area and forming a sphere, the most compact shape possible. Section 7. Hydrodynamics in action, from ships to bloodstreams. Hydrodynamics is more than just a theoretical science confined to textbooks and laboratories. It's a fundamental force that shapes our world, from the grand scale of ocean currents to the intricate workings of our own bodies. Understanding hydrodynamics allows us to design more efficient ships, predict the weather, and even develop life-saving medical technologies. One of the most visible applications of hydrodynamics is in ship design. The shape of a ship's hull is carefully engineered to minimize drag and maximize its efficiency as it moves through the water. By understanding the principles of fluid flow, naval architects can create ships that glide through the water with minimal resistance, reducing fuel consumption and emissions. Hydrodynamics also plays a crucial role in meteorology. Weather patterns are driven by the movement of air masses, which behave like fluids on a large scale. By using sophisticated computer models that incorporate hydrodynamic principles, meteorologists can predict the path of storms, the formation of clouds, and even the long-term trends in climate change. Within our own bodies, hydrodynamics is essential for life itself. Blood, a complex fluid, flows through our arteries and veins, carrying oxygen and nutrients to our cells. The principles of hydrodynamics help explain how blood pressure is regulated, how blood clots form, and even how cardiovascular diseases develop. Section 8. Tapping into the power of flow, Hydrodynamic Engineering. Hydrodynamic engineering is the art and science of harnessing the power of fluid flow for practical applications. It's a field that pushes the boundaries of innovation, constantly seeking new and ingenious ways to utilize the principles of hydrodynamics to solve real-world problems. One of the most exciting areas of hydrodynamic engineering is in the development of renewable energy technologies. Hydroelectric power plants, for example, harness the kinetic energy of flowing water to generate electricity, providing a clean and sustainable source of power. Tidal power plants operate on a similar principle, utilizing the rise and fall of ocean tides to generate electricity. Hydrodynamic engineering is also playing a crucial role in the development of more efficient and environmentally friendly transportation systems. Engineers are designing cars, airplanes, and ships with streamlined shapes that reduce drag and improve fuel efficiency, minimizing their environmental impact. In the medical field, hydrodynamic engineering is leading to breakthroughs in drug delivery, artificial organs, and medical implants. For example, researchers are developing microfluidic devices that can mimic the flow of blood in capillaries, allowing for more accurate drug testing and personalized medicine. Section 9. The Future of Flow. Navigating the Currents of Innovation. The study of hydrodynamics is far from over. As we delve deeper into the mysteries of fluid flow, we uncover new questions and unlock new possibilities. The future of hydrodynamics is brimming with potential, promising to revolutionize industries, solve global challenges, and deepen our understanding of the natural world. One of the most exciting frontiers in hydrodynamics is the study of microfluidics, the manipulation of fluids at the microscale. Microfluidic devices hold immense potential for applications in medicine, chemistry, and materials science, enabling researchers to perform complex experiments and develop innovative technologies on a tiny scale. Another promising area of research is in the field of bio-inspired design, where engineers are drawing inspiration from nature's elegant solutions to hydrodynamic challenges. By studying the streamlined bodies of fish, the flight patterns of birds, and the intricate designs of seashells, engineers are developing new materials, structures, and technologies that mimic nature's efficiency. As we continue to explore the fascinating world of hydrodynamics, we can look forward to a future shaped by the power of flow, where innovation and sustainability go hand in hand. From harnessing the ocean's energy to developing life-saving medical devices, the possibilities are as vast and ever-changing as the currents themselves.